Hello, everybody. It's 9:30 here in Colorado, and it's time for a seminar. Welcome to the 2022 ACOM Seminar Series. It's an honor and a pleasure for me to introduce to you Dr. Justin Holmes and Dr. Stig Hellebust. Justin is professor of nanochemistry in the School of Chemistry at the University College Cork, or UCC in Ireland. He's also a principal investigator at the Environmental Research Institute in UCC and deputy director of the Advanced Materials and Bioengineering Center based in UCC and Trinity College Dublin in Ireland. Justin leads the Materials Chemistry and Analysis Group, researching new materials for electronic, energy, environmental, and catalytic application, addressing key challenges in nanoscale science and sustainability. He currently coordinates two EU projects, Translate, aimed at creating platform for effectively convert waste heat into electricity, and Radical, the topic of today, which is focused on developing a local sensor to electrically detect short-lived atmospheric radicals. Stig is an atmospheric chemist and environmental scientist working at the Center of Research in Atmospheric Chemistry at the University College Cork. His research interests have focused on source apportionment of atmospheric aerosols and automated detection of bioaerosols. He has been involved in a number of projects spanning a range of interests, such as linking air quality and health, emissions from upland wildfires, biological aerosols in the atmosphere, and low-cost sensor network for improved air quality forecasting. And of course, Radical, the project they're going to talk today. Today, Justin and Stig will be talking about Radical, which aims to develop sensor to electrically detect atmospheric radicals and other gases. And they're going to show us some preliminary results and lessons that they've learned from the work they've done so far. Before starting, I'd like to remind you that you can type in your questions at any time during the talk in the space below the video you're watching right now. And I'll be reading those questions at the end of the talk to the speakers. And with that, I introduce to you Dr. Justin and Dr. Stig. Guys, please take it away.
Thanks, Alessandro. Thanks for the introduction. So delighted to be giving this talk. I'm a materials chemist, so it's a bit strange of me giving a talk to atmospheric chemists and physicists and scientists, but here goes anyway. So I'd just like to give you really an overview of the project that we're coordinating in Cork to develop develop a platform to detect atmospheric radicals. Okay, so I will give an overview, project overview, tell you a bit of the kind of aims of the project, and Stig will then go on to kind of talk more about some of the initial results that we've got. So the Radical project itself is a European funded project, funded under what was the Future and Emerging Technologies program. And it comprises people from universities across Europe and one SME. So in Cork in UCC, where this photo was taken, and this is the members of the consortium, although Stig is missing on this photo. We comprise of material chemists, the group which I lead, and atmospheric chemists, the group led by Stig and Professor John Wenger. Excuse me. And also linked to UCC is project management, UCC Academy, and UCC Academy help us, manage the consortium, but also involved with the communication side of the project. Also involved at the University of York, and their job within the project is to look at the surface chemistry. So once we have a device, they actually functionalize molecules on the surface to capture radicals, and hopefully selectively capture certain radicals such as hydroxide radicals and nitrate radicals. In Dresden, the group at HZDR consists of electrical engineers and physicists, and are making some of the devices, the platforms I will talk to you about today. SmartCom is a SME, small company based in Bulgaria, and their role within the project is really computational modeling, but computational modeling in terms of device optimization. And then in Athens, a group, again, on the computational side, physics modeling side, but looking at the interaction of functionalized surfaces with radicals and with other molecules. So why are we interested in radicals? Well, why is a materials chemist interested in radicals? Well, this kind of comes from discussions, all the best discussions that you have over a cup of coffee. And we were working with sensors actually in solution phase, and a discussion with a colleague of mine, John Wenger, and he said it would be great if we could detect radicals. And so we thought, okay, look, we'll give it a go. And we're primarily interested in detecting the hydroxyl radical, but also nitrate radical. And as most of you know probably better than I do, in terms of the importance of the hydroxyl radical in terms of cleaning primary pollutants within the atmosphere, but then at high concentration, you can get also I suppose secondary pollutants forming. But in terms of these radicals are short-lived, very reactive species, and to get a handle on the chemistry that's taking place, during the daytime with hydroxide radicals and nighttime with nitrate radicals, will help us understand more the reactions are taking place in the atmosphere, and then ultimately mitigate for pollution. So from my perspective as a materials chemist, we want to try and detect radicals. So what are the challenges with detecting radicals? Well, in terms of their short lifetimes, seconds is typical for hydroxyl radical. So they don't last very long in the atmosphere, very low concentrations. So, they're difficult to detect. And the main ways of detecting radicals at present is using spectroscopy, which is often cumbersome and can be expensive and I suppose not remote, right? In terms of not mobile, you have to have it in certain locations. And so there's only a few labs worldwide that can detect radicals directly. The methods for direct detecting them indirectly, but in terms of direct detection, it's not routine. So what we want to do in radical is we want to look at a way to use a sensor, electronic nose or smart sensor to detect atmospheric radicals. And we want to do it on a silicon technology, make it cheap, and have lots of these devices that we can deploy globally. So that's the kind of aim of the project. So in essence, what we're trying to build is an electronic nose to sniff out radicals in the atmosphere. So we have our source of radicals. We want to detect, like the receptors in the nose, we want to have some kind of sensor, a functional layer where we can trap these radicals and detect what the radicals are. We collect the data through data acquisition, and then using things like machine learning, we develop a signal, or we have a signal which is specific to a specific molecule or a radical. And that's the kind of way the project is going. So how will we achieve this? Well, I guess this is a schematic here of our devices. So in the bottom left-hand corner here is a scanning electron microscope image of the devices we're using. And so you have the contacts here, a source and drain. You have a contact at the back to gate, or in other words, control the movement of electrons through these very small wires. It's very hard to see there. And this is something that is being developed in Cork, is called a junctionless transistor. And this is one platform that we're using to detect, or trying to detect, atmospheric radicals. So, and the thing about these types of devices, these transistor and the junctionless transistor device, is that you can make these nanowires very small and increase their sensitivity. So what we then do is we have these wires on the surface, we put a functional group that can attach, or sorry, that can bind with the radical species on the surface. And when the radical reacts with this molecule or attaches to it, you generate a dipole moment. And this dipole moment is what we are detecting within the wire itself. Now, this functionalization that is kind of taking place, or that we're doing on these nanowire surfaces, that's guided by our theoretical calculations. So we've looked at, or the group in Athens, I should say, Leonidas has looked at reactions of hydroxyl, nitrate, radicals, ozone with different alkenes and alkynes to try and maximize the dipole moment change that we can detect electrically. Now there's a video here, I don't know if it'll work, but some of the simulations, this is looking at hydrogen extraction, but he's looked at different silicon surfaces and silicate surfaces and how molecules and radicals interact with these surfaces. So once we have this functionalization layer, we react with radicals, we get a dipole moment change, we then measure these different parameters. And we test these devices in an atmospheric chamber to see if what kind of level of sensitivity we have with our devices. Now, I guess this is based on some previous work. So previously we've used these silicon nanowire junctionless transistor to detect proteins in liquids, and here shows again on the right, this image is a scanning electron microscope image of an array of nanowires, and what we're able to do is actually detect down to zetamole concentrations with these devices. But the goal is to then transfer our knowledge from this liquid phase into a gas phase and to detect species of radicals, which are often very low concentrations and very fast reacting. And Stig will come on to talking about the approach for using machine learning to help us with the detection. So in terms of overall the project, the radical project, so I guess these are the different steps. So in terms of fabricating devices and modeling, that involves our partners in Dresden and in SmartCom. The organic functional layers on the surface of the nanowires has been done in York, in the chemistry department there, and simulation of the best layers for putting on our devices has been done in collaboration with University in Athens. Optimizing these, we make these sensors and we're testing them and optimizing them within UCC in Cork, and also what we're also doing is we have the atmospheric chambers within Cork, which we will test we are testing our devices in, and ultimately test them outside. And then in terms of communication, developing or dissemination of our work, this UCC Academy are involved with that, and looking for future funding and collaborations. So these are the chambers that we are working on at the moment. So on the left shows the atmospheric chamber for that we're using to test our current devices. So it's about 6.5 meter cube volume. It's under atmospheric pressure and temperature. There is some control of humidity, but we actually want to use this, or this is a good chamber for our initial tests. There is the Irish atmospheric simulation chamber also in Cork, which is a much bigger volume chamber. You have better control over temperature and humidity, and you can generate nitrate and hydroxide radicals in situ. And Stig, I think, will probably talk a bit more about that. So ultimately, when we've developed our sensor, we want to then move to this, in the smaller chamber, move to the larger chamber, where we can compare or even calibrate our sensors with spectroscopic methods. So these are the ways that we interface into the chamber. There's these sensor mounting platforms, which are printed circuit boards, and we just attach them into our chip holders, and then we have these rods which go inside the chamber. The cables connect to our electronics, and then we can measure a signal. We also have an Extron probe station, which is not much used for radicals, but is useful for other gases, where we can flush or flow gases over a chip with probes, electrical probes, and we can measure a change in the conductivity or other parameters within our device. So they're the kind of two setups that we're using at the moment. So in terms of, I guess this project is kind of halfway. We haven't done anything in terms of radicals yet, although we're developing the functionalization chemistry for detecting radicals. We're actually developing the sensors now for detecting radicals. But to start with, really, we just wanted to look at and see if we could detect anything with our sensors. So the first thing that we started to look at was NO2, and this is because we had NO2 in the lab. This kind of here, I guess, is where we're trying to validate. Can we actually see anything with our silicon junctionless transistors? You know, and using NO2 as a kind of calibration gas or test gas. So if you look at the top left, you can see the type of device we have. We have a silicon nanowire, we have gold and nickel contacts, and under that we have a silica layer, and we have a gate. And what we're actually doing here to test our devices, we're not testing with any organic functional groups on the surface to trap radicals. We're just testing our device with an oxide layer. And this image in the middle shows a cross-section of a silicon nanowire. And you can see on the top of this wire, I don't know if you can see my cursor or not, but the silica, what we're doing is we're just changing this SiOx layer. We're just changing the thickness of that and looking at the response from our devices. So we have a native oxide which grows naturally on the silica, so it's around 1 or 2 nanometers, and then we can thermally grow a thin oxide layer, which would say is 3 nanometers, or a thick oxide layer, which is 10 nanometers. And we want to see if the interaction with NO2 at the surface gives us any kind of change in signal in our device. And this is kind of based on a lot of theoretical studies where researchers have looked at the interaction of NO2 with silicon surfaces, and you see this dipole moment change. And what we can see down here in this bottom left is a plot of drain current versus gate voltage. And you can see in the presence of 25 parts per million NO2, we see a signal. And then in 0, where we see a lower signal. So we're now starting to see an increase in this current, hole-mediated current, when we have an NO2 atmosphere. So, you know, can we use this as a sensor? And these are kind of the initial sensor tests upon NO2 exposure. So we got no functional groups here. So we're not looking at particularly selectivity, but we just want to see, can we get a response? And our devices, we have what we would call the N-type devices, so they're doped with silicon doped with phosphorus. But what happens is NO2 absorbs on the surface of the junctionless transistor, the nanowire part of the transistor, which is the channel. It accepts electrons from the surface, and it causes a change in the conductivity of the channel. And these devices, or sorry, this NO2 absorption leads to an increase in the carrier concentration. When we're looking at P, that's the red line. So leads to an increase in conductivity on the P side and a decrease in conductivity on the N side. So what we need to do then is, you know, is this data meaningful? Are we seeing any real effect of the NO2 is having on the device? And I think that's where I hand over to you, Stig. So I'll stop sharing.
Yes, hello. Thank you, Justin, and hello, everybody. It's great to be talking to you. I can't see who I'm talking to, but I'm used to that at this stage. So I'm an atmospheric chemist, so I often talk to atmospheric chemists, but never about materials chemistry. So this is a new experience for me as well. Now, so to pick up where Justin left off, I'll take you through some of our preliminary results and a little bit about our experimental procedures and design and how we're going with that. So looking at this diagram of the nanowire, the signals that we want to measure from those, they are influenced by several things. And the sensing part of it is the chemical interaction between the nanowire surface and the target species in the gas phase. But the signal that we measure is influenced also by the physical parameters of the wire, the dimensions of the wire, the thickness, the length, the material that it's made of, and the oxide layer that Justin explained about the oxide layers on the surface. So for the calibration, we have to study not just the sensing part of the signal, but also all the other interferences. So the signal looks like this. It's basically a drain current versus the gate voltage, and this is what is measured every time you test the device. And from this, we extract a number of features that we work with. And first one is the slope of the linear part of that curve. That tells us something. It's called transconductance. Don't ask me about that. Justin can explain these things later. There is the maximum current that you can get through the device. There is where that slope meets the baseline is what we call the threshold voltage. So far we have three things, and this depends on the shape of that curve. So it's essentially the shape of that signal, that measurement, that lets us extract the features of interest. But from these three, there's also three more. Justin mentioned the carrier concentration, and we have something called mobility, and then there is something called the sub-threshold slope. So down in this low region here, if we look at it on a logarithmic scale for the drain current, there is another slope, which turns out to be quite important. So from this now we have 6 features times 2, because these devices are ambipolar. So we have 12 features to start with, and then got to figure out which ones of these are actually useful for the sensing and the calibration part. Because some of them depend directly on the surface chemistry, some of them depend directly on the other parameters, and hopefully they'll all tell us something about the target species. So we have something like this, a profile of different signal responses for each wire. So these wires, of course, you can reproduce them, you can make them identical. So you can pack a lot of them in. And the idea then is that you can make the surface chemistry different on every one of them. So you get not just one of these profiles, but you get as many as you can put onto the chip. So that's great, but the issue then is that any one of these signals, like I said, they depend on the shape of that curve that we measure. So when you increase the concentration of something, that will change a lot of those features, but not necessarily in a linear way. It's the effect it has on the different features is not necessarily additive. And then you have interferences with other gases and environmental conditions, temperature, all of that. So it's not just the chemistry of the interaction that determines that signal. And it's also not given that a higher concentration just extrapolates to in the same direction of that signal. So these are all things we have to figure out. So so if I take you through some of the tests we've done with the oxides that Justin explained, we have native oxides, we have thermally grown oxides, and different thicknesses. So we might measure a set of features on one of those oxides. Let's say the native one first. You change the oxide layer and do the same test, and you get a different set of features. That's fine. And then you try with a different thickness of that layer, and you will get a different set of features. But the features will not necessarily change in the same direction. Some of them may not change at all. And so far, we still have only tested in clean air, say, and zero air. So let's say we add some NO2, and you get a response from the different signal, a different profile. But it's not given that same, if you expose it to that same gas concentration, if it's a different thickness of that layer, you could get a completely different profile of those responses. So these are all things that we have to investigate. And here, if we just have three parameters: oxide type, thickness, concentration, you end up with at least 8 different tests to do. And of course, we have to start looking at all the different organic layers, how they all interfere, how they all respond to other gases, because of course the atmosphere is full of interferences, and all the environmental conditions. So the testing requirements, they grow exponentially. So we have to make sure that the experimental design, of course, is suitable for use. But the experimental burden falls to Aishali, a PhD student at UCC, and Suba, who is a research fellow on the project, and they have done a lot of testing already. The testing proceeds in actually four stages. So it starts out with this little probe station, which allows you to expose the device to a gas. It's a sealed probe station, so you can control the gas concentration. We have the chamber that is the six cubic meter chamber, where you can have the measurements. This is probably the only atmospheric simulation chamber with the capacity to measure electrical signals from the atmosphere. If there are any other ones, I'd love to hear about them. So we have the probe station and the small chamber, and we also have the big chamber, the Irish Atmospheric Simulation Chamber, which is EASC for short. EASC in the Irish language is actually a word that means fish. So locally, people sometimes refer to it as the fish tank, but there are no fish in it. It's a 27 cubic meter chamber. And in this chamber, we actually can detect radicals directly. There is a unique spectroscopic setup. We have top sims and all the standard instrumentation. And I'd just like to mention that anybody can use this facility through the transnational access that's funded by the EU. So if anybody would like to come and do some experiments, bring their own instruments, have access to all our instrumentation, please get in touch. So that would be the third stage of the testing. And of course, the final stage of the testing will be the real atmosphere. And for that, we'll use our atmospheric monitoring station, the air quality monitoring station in Cork. So we've done some tests, and you get a profile of measurements, and then you want to see, can you see any difference? Is there any difference now? Here on the left, I have zero air. On the right, I have 50 ppm of NO2. And then the question is, can you tell from the measurements that there is a difference in concentration of NO2? Because a sensor, of course, is all about sensing something. But we can have a closer look at some of these measurements. Like I said, the shape of that curve. So, for example, if you look at the slope of that IV curve and the subthreshold slope, which is what I have here in these two variables here. We have the slope and the sub-threshold slope. It turns out that this actually allows us to separate the native oxides from the thermal oxides. And it turns out that the sub-threshold slope is also an important parameter in separating the different oxide thicknesses of the layers. So that's useful information that we can bring with us when we are continuing to develop the surface chemistry of these, but it doesn't get us anywhere in terms of predicting the NO2 concentration. And of course, the purpose of radical is not to detect and predict NO2 concentrations, but we're not there yet that we're testing it on radicals. So as a proof of principle, we are experimenting with what we have, which is NO2. And what we want is to develop a way of using the features extractable from the electrical measurements to predict the concentration. And I'm sure you all know where I'm going with this. We have to go to the chemistry toolkits. The multivariate calibration is something we've been doing in chemistry for a long time. There's been a discipline called Chemometrics for at least 4 decades. Nowadays, everybody calls it machine learning, but chemists have been using these methods for a long time. And the task that we are facing is really nothing more than finding the right combination of experiments and analytical methods so that we can develop a robust calibration model that will take, because we know there are signals here that that are related to a number of interesting parameters, but it's about making it robust so that you are predicting what you want to predict. So I'm not going to take you through all of these different attempts. I will give you a quick example of what happens if we put this through, say, a decision tree model. A decision tree is simple, but conceptually a simple supervised learning method where you take your data sets, you have several variables, and you put it through a number of tests, and you have a training data, and you end up with a prediction of a concentration from multiple inputs. And of course, there are many other ways of doing this, and we will try them all. But the decision trees, then of course you can do random forest, you can do various variations on that. So if we try something called a gradient boosted 3 discriminant analysis, it comes up with a prediction. And let's say, let's not be too ambitious to start with. Let's just say, can we distinguish between tests where the device was exposed to 0 air and the test where it was exposed to NO2, and never mind the concentration at this point? And the answer is yes, because if we what this model comes up with is a probability of prediction, and it turns out that of all the 106 tests that we have done here so far, they were all classified correctly as relating to NO2. So of course this is a simple system. It's either 0 air or 0 air with some NO2 in it. But what's interesting as well is that we can look at what are the important variables. And again, it turns out that for this particular model, the shape, the slopes seem to be the most important parameters here. So this is something we can bring with us maybe when we are looking at surface functionalization. But we can, this went well, so we can be a little bit more ambitious and look at actual NO2 concentrations, same model, and it's the same result really. If you look at the concentrations that we actually tried and the concentrations that are predicted, there are only 4 out of 106 tests that were misclassified. And those were all the native oxides. So I think this is promising. Of course, we still have to try it with radicals, but again, it's instructive to look at, to understand what is actually happening in terms of the chemistry and the interaction. It's instructive to look at the features that seem to be important in this prediction. So I think at this stage, this is early stage, we're talking to you before we have really most of the testing done. But I think at this stage, we do see that the gas phase and the nanowires interact in such a way that we can extract useful features from that. We want obviously to work on the selectivity, and for selectivity, it's important that the response has a certain magnitude, and also that the signal is quite stable. And we've seen that the surface coating will influence both of these features. So we have a lot of work ahead, but I think it's going the right way. So I'm going to hand back to Justin.
Okay, thanks, Stig. So I guess just to finish off with, I suppose, you know, as Stig said, we know these are initial experiments that have been done on NO2. Within the next year, we hope to, I suppose, translate some of this work to detecting radicals, and the future vision, and the way we kind of sold it to get the funding, I guess, is that we want to have a kind of global network of sensors, you know, more than just in 1 or 2 locations around Europe, which will give us a better understanding, really, the role of radicals. Hopefully we'll a better understanding the role that radicals play in air quality regulation, and also you know, as a way for to improve air quality forecasting. And you know, who knows, there may be some other using this platform which we're developing for radicals, potentially can be used for other gases. We've already shown that there's some detection with NO2, but you know, potentially could be used for the whole range of gases, multiple systems. Next one, Stig.
Yeah.
Thanks. So you know, we're researchers, and we're also always interested in getting feedback and talking to people about potential applications of our sensors. We particularly, you know, really interested in collaborating. If anyone wants to get involved or come over to Cork for a visit and you know, get in on. Stig was talking about the atmospheric chamber that's available to use, and also we would like to, you know, possibly use these electronic sensors once we've had them outside of the research community. But yeah, of course, we'd love to have hear your ideas. You know, if you want, like I said, if you want to come to Cork, or you want to get, you know, some suggestions of other gases that we might try in our chambers or other things. But yeah, I guess that's it from us. So thanks very much. I guess we just got questions to answer now.
Thank you so much. This is really interesting. I really love this project because it puts together 2 different fields of science, material science and atmospheric chemistry, and tries to do something really hard, because measuring radicals, for whoever has at least seen people measuring them, knows that it's a really complicated and tricky business. It's cool to see your preliminary tests and the application of machine learning to try to tease out what's important. And yeah, I really appreciate it, and I'm looking forward to see what you guys come up with. So what's like, what's your end goal? Like, what would be your ideal timeline for getting a sensor out, for example? Like, how long is the project at the moment, at least?
So the project is 4 years.
And you're at year, which year are you in now?
Oh yeah, sorry, we're just coming to the end of year 2.
Okay.
So the idea is that by the end of the project, we will have a sensor to detect radicals. If that works, then I guess, you know, hopefully we can take it further. But by the end of year 4, that's the kind of aim, to have a sensor to detect radicals. Now, you know, what radicals and at what concentrations is another matter, but you know, that we have some electrical way of detecting atmospheric radicals.
Yeah, I mean, that would be already quite an impressive achievement, honestly, especially you know, given the size of the sensor. And you know, even if you find out how to measure really well NO2 and really selectively at a low mixing ratio, would be already pretty great.
Yeah.
So we have a question from the audience. Randy asking, I wonder if hysteresis might be a challenge because of the sticky nature of many molecules and reactive nature of radicals. Any thoughts on this?
Yeah, I mean, it is a concern. Now, in terms of, I guess one thing that we're trying to kind of do is optimize the functional layers to kind of minimize well, to get the best interaction with a particular radical. So at the moment, we've been looking at things, the hydroxyl radical and ozone. You know, I mean, within the sensor, we want to see a dipole moment change. The only issue that we might have is at high, say, when we're first doing our experiments, if you have such high concentration of radicals, they might just eat the surface completely. That's one thing. And the second thing, I guess, is in terms of, you know, I guess we're not, or we're trying to, can we make a reversible sensor? But at the moment, we haven't done that in terms of the organic part. So the radicals come in, they interact with the functional group, and that's it. But ideally, yeah, I mean, it is a challenge. I mean, there's a lot of challenges in terms of the radicals. What we actually have seen with the functionalization part is, you know, at high concentrations, you almost get this kind of domino effect where one radical comes in, or a few radicals come in, and then the whole surface is eaten up by radicals, right? So it's like, how can we maximize the time in which the sensors last for detecting these species? I don't know if that answered the question or not, really.
Yeah. I think we did some calculations on this, because the sensor, say, in principle, doesn't have to be reversible. If it was a question of taking it out of a tube, exposing it, and getting one reading, that would still be a good result. But obviously, it would be better if the sensor could be used for longer than that. And we did some calculations on the concentration of radicals in the atmosphere, and I can't remember the figure now, but it's if the surface reacted only with radicals, it would take I think it was a matter of weeks at least before it was all spent. But at some point, the way we are going, we're working on surface chemistry that will be consumed by the radicals.
So is the algorithm, maybe another way to put this question is the machine learning algorithm time dependent or not? Like when you do you know, measurement 1, are you still using the same sort of functions to invert your you know, your complicated space than at measurement 10?
Yeah, that's a really good question, because we don't know yet, because the fact is these scans, they take a few seconds, right? And if you have a reversible situation or a non-reversible situation, if you have a device with many arrays on it, they all have to be measured. Are they going to be measured in sequence or simultaneously? And if they're measured in sequence, then they're measuring a different situation. But you, so we have to work that out. I mean, because there is the actual concentration, and then there's the change in concentration. And it might turn out that it's better to work with the change in concentration in terms of the algorithm. But yeah, so these are things we'll have to figure out.
Cool. So Andy is asking, how linear is your approach? For what concentration range do you get a linear response? And is there adsorption, desorption reversible? I think we're sort of.
Yeah, so I don't know whether you want to answer that, Stig. I mean, for the moment with the NO2, we've just been looking, so there's no functionalization there. So that is purely based on absorption and desorption. So you can either remove that layer through heating, but over time, you know, so in the chamber, what we've done is pass zero air over it, and then the absorption, or NO2 absorbs from the surface. We haven't done anything with the radicals yet.
Yeah, again, I don't think we will have a linear response, really. And also there is the reaction time. And I think you could see from the plot Justin showed there with the timeline of the NO2 at different concentrations. So for this particular system with just the oxide and the NO2, it looks like it's reversible, but also there's a slow kind of regeneration.
Yeah, this is all done at room temperature, right? So unlike, say, metal oxide systems where you may do it at a higher temperature. So this is all done at room temperature. So you can, in theory, provide a bit of heat to desorb the molecules, or the NO2 anyway in this case.
So how many of these wires do you have on the sensor you put in the chamber?
So I had a slide, and I didn't actually refer to it. It's in like a plastic holder, and it showed these little blue squares that are 1 centimeter by 1 centimeter, and within those you have 32 devices which you can contact. But within each device, you can have you can change the number of wires you have within each system. So within each device, I can have a single wire, or I can have 10 wires, or I can have 100 wires, right? So this is something to optimize as well. And you can put one device next to another. One may have one functional group, one may have another functional group. And try to develop this kind of fingerprint, which is what Stig is doing, to identify the molecules. But the key thing with these devices is really how thin this channel is, this nanowire channel. So the smaller you can get that, say below 10 nanometers, the more sensitive the devices should be.
Cool. Very good. Let's see if a few other questions come in. Because now I don't know wires, but and I don't know a lot about material applications, but I think there are technologies now that manage to go down to a few nanometers, something like maybe 5 nanometers. At least you see on those nanodots that sometimes you see, 3 nanometers, 5 nanometers. I'm not sure exactly what they're measuring. Do you think that those wires will be able, say, in a few years to go down from 10 to 5?
Yeah, I think they will. I mean, we can get down to 10 relatively easily. I guess what there are a lot of systems out there, so you can look at two-dimensional materials, carbon nanotubes, and all those type of wires that people synthesize. But the thing with these devices, it's done in a silicon fab. So you're using all the technology that is being used to make microprocessors that are used for chips in computers and phones. So it's very well developed and relatively well, it's very reproducible and relatively cheap at a large scale. So that's why we've kind of gone for this silicon technology rather than some more kind of exotic types of materials. Although we are also looking at 2D materials, molybdenum sulfide, those type of materials. But yes, so you can get down below 10 nanometers already.
Okay, and how does the sensitivity changes with size? Is it linear or quadratic?
So I mean it changes. How it changes depends on quite a few things. I mean, you're increasing the surface to volume ratio, so you get a much better sensitivity. There are other things that kind of come into play there as you get down to very small sizes in terms of good contacts, leakage, currents, and those type of things. But with the kind of back of the envelope calculations that have been done by the group in SmartCom suggests, and in Dresden, that below 10 nanometers we should be able to detect these dipole moment chains from radicals at relatively low concentrations, so parts per billion and lower. So that's kind of where we're aiming for, that kind of those dimensions really.
Sebastian says, great talk, Steve and Justin. Any thoughts on how much trust should we put in the complex black box algorithm to correct the measurements? At what point the process data stops being a measurement?
Will I answer that?
You, Stig. Yeah.
So yeah, no, good question. I wouldn't trust a black box at all. I never trust an algorithm I didn't understand. And we have the advantage of starting with nothing. So we control the experiments and we control the information so that we can design our experiments to fit our algorithm, right? So at every point we're trying to extract features and information, and then we try to understand why do we see. I mean, multivariate calibration has been used in chemistry for several decades, and it has a basis in the measurements and the data. So in any model, of course, you have to make sure you don't do overfitting, and that's something that we have to be aware of. But it has to come back to the features. So we can't just treat these features but we have to understand why that feature changes in that way. So these chemometrics methods, they just allow us to extract those patterns. It's just about finding those patterns and finding the important features or measurements, and then we take it from there. So I think it's a really important point that is being made there. We can't just trust a black box algorithm. You have to understand why it works.
Yeah, and then you're adding a dimension per other gas that you might be slightly sensitive to as well. So it's
so the experimental design has to be really carefully planned, so that's because if you were to it grows exponentially.
Yeah,
if you want to get all the interactions and interactive features and that, but yeah.
Okay. Okay, just some admiration for your work from Shane. Thanks, Shane.
It must be an ex-student of mine, I guess.
All right. Yeah. So we're a bit early today, but thank you so much for being open to sharing your results and talking to us. It's a really cool project. I really I'm really looking forward to see where you guys get to. Thank you very much for everybody who tuned in, kind of relatively early in the morning here in the US for listening to the talk, and see you next time. Bye-bye.
Thanks very much.
Thank you.
Bye.
Bye.